In a noisy sugar factory set amid tropical cane fields, there is a peculiar moment few people ever notice. An amber-colored liquid simmers inside massive metal vats. Steam rises into the humid air. And then, almost like an ancient ritual, white crystals begin to form. They crystallize slowly, shimmering like artificial snow in the tropics. Workers collect these white sugar grains, pack them into sacks, and ship them across the globe. But what remains in the vat? A thick, nearly black liquid, carrying the scent of smoke, earth, and metal. It is not called essence, it is labeled a byproduct. For centuries, we have celebrated purity. White has been equated with cleanliness. In chemistry, crystals symbolize order. But what if the portion we discard actually contains more biological information than the flawless crystals we treasure? Welcome to the world of molasses, where science compels us to reconsider a fundamental question: is perfection always the highest value? To understand molasses, we must begin with sucrose, a molecule composed of two units, glucose and fructose, joined by an alpha-12 glycosidic bond. Imagine sucrose as twin molecules locked together in a stable configuration, highly soluble in water due to its polar hydroxyl OH groups. When sugarcane is crushed and its juice concentrated, the solution gradually approaches a state of saturation. Here, physics enters the scene. As more water evaporates, the solution surpasses its saturation threshold and becomes supersaturated, an unstable condition. Like a crowded room waiting for a door to open, the sucrose molecules are forced to escape from the solution, linking together to form a repeating geometric crystal lattice. Sugar crystals are the result of molecular self-organization, a form of chemical order. But not everything can join that network. Minerals such as calcium Ca²-, magnesium Mc², and iron Fe², along with complex organic compounds, organic acids, proteins. Phenolics cannot fit into sucrose's precise crystal structure. They are excluded, left behind in the remaining liquid. Molasses is the portion that cannot crystallize. If white sugar is like a text file compressed to its smallest possible size, containing only pure sweetness, then molasses is like a hard drive, storing the entire biochemical history of the sugarcane plant. It preserves traces of soil, sunlight, microorganisms, and the agricultural environment. Thus, the first paradox emerges. What we call impurities may in fact be the most information-rich component. After crystallization, the mixture is transferred into a centrifuge, a machine that spins at extremely high speeds, generating forces thousands of times stronger than Earth's gravity. Imagine sitting on a massive rotating ride. The heavier objects are flung farther outward. Inside the centrifuge, the dense, solid sugar crystals are forced into a separate chamber. The thick liquid that remains is molasses. But why is it black? The answer lies in phenolic compounds and oxidation products. These molecules often contain stable aromatic rings, carbon structures capable of absorbing visible light. As they accumulate, they absorb most wavelengths and reflect very little, producing a deep brown to nearly black color. Additionally, iron ions can form complexes with organic compounds, intensifying the dark hue. Molasses is not merely unrefined sugar. It is a multi-component solution, where each molecule tells its own chemical story. And here we encounter a symbolic stratification. The orderly structure crystals is separated and elevated as the standard. The heterogeneous mixture liquid is retained as residue. Yet in biology, diversity is the source of resilience. An ecosystem composed of only one species is an ecosystem prone to collapse. The production process does not end with a single boil. Sugarcane juice can be concentrated and crystallized up to 3 times. With each cycle, the remaining sucrose content decreases, while the molasses becomes progressively thicker, darker, and less sweet. At the blackstrap stage, the third boil, most of the sucrose has already been extracted. What remains is a dense mixture rich in minerals and thermal reaction byproducts. As temperatures rise, two crucial chemical processes occur: caramelization and the Maillard reaction. Caramelization is the thermal decomposition of sugars, forming complex polymeric compounds such as caramelin and caramelin, large molecules that strongly absorb light and generate bitter notes. The Maillard reaction, occurring between reducing sugars and amino acids, produces hundreds of aromatic compounds, including furans, pyrazines, and melanoidins. These molecules are responsible for smoky, coffee-like, and toasted bread aromas. Blackstrap molasses is no longer failed sweetness. It is the result of thermodynamic chemistry, a restructuring of molecules under heat. If white sugar is a single musical note, blackstrap molasses is a symphony layered with bitterness, subtle salinity, metallic tones, and smoke. This extreme concentration reveals another paradox. The further a substance moves away from purity, the more sensorially complex it becomes. So why does molasses provoke a stronger reaction than white sugar? On the tongue, sweet taste is detected by T1R2, T1R3, receptors transmembrane proteins specialized in recognizing sucrose. White sugar primarily activates this system alone. Molasses, however, tells a different story. Beyond sucrose, it contains mineral ions and bitter compounds that stimulate T2R receptors, the evolutionary warning system designed to detect potential toxins. When sweetness and bitterness appear simultaneously, the brain must process conflicting signals. This contrast activates broader neural networks, including the dopamine reward system. That is why molasses can leave a deeper impression. Even though it is technically less sweet, in sensory psychology, complexity creates depth. A single note is easily forgotten. A layered chord lingers. Molasses is a chord. It reminds us that taste does not merely seek maximum sweetness, it seeks dimensionality. Modern industry has been built around the idea of refinement removing, whitening, standardizing. In that process, molasses was labeled as residue, excess, waste. Yet from a scientific perspective, molasses is not the failure of crystallization. It is evidence of abundance. White sugar symbolizes order, a perfect yet simple structure. Molasses symbolizes mixture, an imperfect system rich with biological information. And perhaps this is the deeper lesson in our pursuit of perfection. We often discard the very elements that give something its original identity. Molasses is not merely a byproduct. It is a reminder that value does not lie in color or purity, but in the depth of internal structure. Sometimes, what is rejected is precisely where nature has stored the most soul.